Hello everyone, my name is Varun. I'm pursuing my PhD in the domain of deep learning for autonomous driving at Value, Germany. Today, I would like to present my paper, OmniDet, a surround view cameras based multitask visual perception network for autonomous driving. First off, I would like to present the motivation behind our work. Near field perception for autonomous driving is a region from 0 to 10 meters and 360-degree coverage around the vehicle. Some of its use cases are automated parking, traffic jam assist, and urban driving. The sensor suite includes ultrasonics, fisheye cameras, and radar. There are limited data sets and very little work on near field perception tasks as the main focus is on far field perception. In contrast to far field, it's more challenging due to high precision object detection requirements of 10 centimeter. For example, if you look at the parking scenario in the figure on the right, the car needs to be parked in a very tight space with partial object visibility and no room for error, requiring very high precision. Four fisheye cameras are sufficient to cover the near-field perception. Standard algorithms cannot be extended easily on fisheye cameras due to the large radial distortion. There is very little work on the perception algorithms on fisheye cameras. Our goal is to develop a level 3 near-field perception stack using four fisheye cameras. Our developed framework is called OmniDet for two reasons. Firstly, Omni can be used for wide-angle omnidirectional cameras. Secondly, the word Omni means all, and we are detecting all the necessary objects. Thus, it is a framework that does a 360-degree near-field detection. The standard question which arises when we talk about distortion in fisheye camera is, why not rectify the images? Most algorithms are usually designed to work on rectified pinhole cameras. The naive approach is rectifying the fisheye images and applying these algorithms. But there are significant drawbacks. Removing distortion leads to a significant loss in field of view, which can be seen in figure where linear rectification is applied on fisheye images. For a horizontal field of view greater than 180 degrees, there are rays incident from behind the camera, making it theoretically impossible to establish a complete mapping to a rectilinear viewport. Thus, the rectification defeats the purpose of using a wide-angle fisheye lens. Resampling distortion artifacts are particularly strong in the edges as a small region in the fisheye image is expanded to a larger region in the rectified image. The texture is lost and noise is also introduced. A few of the most important questions and challenges that arise for near-field perception are answered by these perception tasks. What is the geometry of the scene? It is given by monocular depth or distance estimation. How are different parts of the scene moving? Motion segmentation. How to identify objects and locate them? 2D object detection. What is around me? Semantic segmentation. Can I perceive the world around me clearly? A scene may be obstructed due to soiling or adverse weather. It can be given by soiling detection. Our work is targeted for large-scale industrial deployment of these tasks in millions of cars. We need to consider critical practical factors such as the model needs to be robust to intrinsic camera variations arising due to manufacturing tolerances. A low-cost embedded hardware is needed for commercial reasons. The performance of these models needs to be real-time for driving scenarios. Model validation and safety certifications are required for compliance. Considering all this into account, we propose to use a single multitask learning model in contrast to using multiple models for different tasks. We shall now look into the details of our proposed OmniDet MTL framework for near-field perception. The red block indicates the self-supervised distance estimation and pose estimation task and its corresponding losses. The green block indicates semantic segmentation followed by motion segmentation in purple. The gray block indicates object detection followed by soiling segmentation on the right. We post-process our estimates to a top view map for a level 3 planning module in the final step. All the tasks here are trained end-to-end, producing a single model for inference. In the further slides, we focus on our main novel contributions. Firstly, our camera geometry mechanism, followed by synergy between tasks, and finally, our contributions in improving each task. In this work, we target the design of a model that can be deployed in millions of vehicles having its own set of cameras. Camera intrinsics can vary due to manufacturing tolerances. The extrinsics can vary widely depending on the size of the vehicle. Even after deployment, calibration can vary due to high environmental temperature or due to aging. Thus, a calibration adaptation mechanism in the model is essential. In contrast, public datasets like Kitty and Cityscapes have a single camera instance for both the training and test dataset. In the Woodscape dataset, there are 12 different cameras with slight intrinsic variations to evaluate this effect. There are 4 cameras around the vehicle with different intrinsics, even for a single instance of a surround view system. We develop a single model for all cameras using camera geometry tensor as the adaptation mechanism, enabling reuse of data from diverse cameras. Main aim is to convert camera calibration to a pixel-wise tensor and feed it to a CNN model to provide camera-specific adaptation. The proposed camera geometry is inspired from CamCons, which was used to provide calibration adaptive depth estimation. Camera geometry tensor comprises 6 planes listed below. Firstly, 2 for the principal coordinates Cx and Cy. Secondly, we derive two planes for the angle of incidence maps AX and AY as shown in the equations. The angle of incidence can capture any arbitrary distortion and it's independent of intrinsic models. In this work, we employ the polynomial camera projection model. We create AX by setting xi to ccx of I, j and yi to 0. And similarly for AY, we set yi to cy of I, j and xi to 0. Finally, we add two planes for the normalized coordinates as used in CamCons. The camera geometry tensor is added at each level of the encoder-decoder structure, which can be seen in the figure below. We can see the effect of a CGT mechanism in this figure. With our camera geometry tensor, the predictions are sharp and scaled to the right depths. Without CGT, the estimates are blurred and wrongly scaled. We also see improvements in quantitative results compared to specialized models for each camera as shown in the table on the right. Most previous works employed hard parameter sharing techniques, that is, a shared encoder that branches out into task-specific heads without any synergy. In addition, our goal is to induce synergies across the tasks in the form of loose coupling, maintaining the tasks to be independent. We achieve this by passing some decoder features from one task to another. The decoder features from the guiding task are combined with the intended task's decoder features using pixel adaptive convolutions that contain an adaptive kernel to mix both the features. For example, semantic segmentation produces holes in the road surface due to irregular textures, and depth maps corresponding to the road surface may help regularize the segmentations. There are multiple instances of synergy where semantic is guiding depth and object detection features and motion is guiding depth during the training phase. We discuss how we solved one of the concrete challenges using synergy, namely the dynamic object issue for depth estimation, which contaminates the photometric loss and causes infinite depth during inference. Our previous work used the dynamic object mask from the semantic segmentation task and employed it during the view synthesis process of depth estimation. The major drawback of using semantics is that it might not cover all the dynamic object classes in the semantic ground truth. Example, cows. Therefore, we propose a robust alternative to enable filtering of the dynamic objects using the motion segmentation task, which yields either a static or a dynamic mask. However, the user can leverage either one of the tasks to solve this issue. The approach is as follows. If we closely look into the figure, dynamic objects inside the segmentation masks, which can be either from semantic or motion task, from consecutive frames in B and D, are accumulated to a dynamic object mask F. F is then used to mask the photometric error E as shown in H. Quantitatively, employing motion segmentations masks yields better results than semantic masks as shown in table. For the architecture, we employ a vector-based self-attention encoder to provide the global features for the network architecture. The encoder is shared for all the tasks. The encoder is also shared over the two streams for motion segmentation and pose estimation, effectively having only one encoder per image. The distance decoder is made robust by using semantic guidance with the help of pixel adaptive convolutions. Coming to the losses of distance estimation, we make use of a photometric error warped for both forward and backward sequences based on a previous work fisheye distance net. More constraints are enforced by adding a cross-sequence geometry consistency loss. This increases the baseline and provides additional consistency constraints during training. Additionally, we incorporate two significant feature metric losses, that is discriminative and convergent loss, to emphasize the homogeneous areas. A standard bounding box is not a good representation for fisheye images. Figure A illustrates how a bounding box fits poorly. Thus, we explore various representations such as oriented box, curved box, ellipse, 4-sided and 24-sided polygon fits. The 24-sided polygon works optimally without significant increase in runtime. The representation accuracy is measured with respect to instance segmentation ground truth. For the 24-sided polygon approach, we perform adaptive sampling of points to create the best fit, which uses more points to represent curves and few points for the straight line. Three of our tasks are formulated as segmentation tasks. Semantic segmentation has 7 classes like road, road markings, lanes, etc. The motion segmentation predicts each pixel to be static or moving. Soiling segmentation detects lens soiling and contains 4 classes, namely opaque, transparent, semi-transparent, and clean. It will enable the trigger of a lens cleaning system for continued operation necessary for the L3 system. We employ Loas softmax loss for these tasks, and motion segmentation additionally employs focal loss. Finally, we will discuss the quantitative result. We perform a quantitative evaluation of OmniDet on 3 different datasets, namely Woodscape, Kitty, Cityscapes. We ablate the single task versus multitask results. We obtained superior results when compared to single task trading by mitigating the negative transfer in our multitask framework. Balancing multitask loss during the training is a crucial problem. In particular, most of the proposed methods were tested on 3 tasks. We explored the standard methods for a 6 task model and proposed a novel variance normalization technique that achieves the best results. It consists of normalizing each loss by its variance over the last n epochs using the equation below. This method is motivated by the simple idea that the task loss values can be seen as a distribution whose dispersion is its variance. A large dispersion leads to a lower task weight, whereas a small dispersion to a higher one. Its final effect tends to homogenize the learning speed of the tasks. Zootscape was recently released with no other reported methods. We evaluate on the standard public dataset Kitty. We achieve state-of-the-art results for depth and pose estimation tasks. PACNet SFM and our approach do not scale the predictions with LiDAR ground truth during test time as we achieve scale-aware depth estimates. This slide illustrates our OmniDet MTL framework's prediction for near-field perception. The depth and semantic segmentation produced impressive results. Motion segmentation had the least mature results and can benefit from the self-supervised flow. For further qualitative results can be seen in the YouTube link below. Coming to the conclusion, our OmniDet framework achieves the necessary modules for a level 3 near-field perception stack. We deployed our MTL model in a test car. The model runs at 60 FPS on an automotive embedded platform, that is NVIDIA's Jetson AGX. We hope that this work encourages further research in building a unified perception model for autonomous driving. For that, we provide our Woodscape dataset and the baseline code to the research community. Thank you for your attention, and please feel free to contact us for further questions regarding the paper, the Woodscape dataset, and our code.